So I'm going to be combining this pink vector and this green vector with a linear combination, and I'm going to be adding scalars. So first I'm going to add some scalars to my pink vector, and I'm going to make it so that way I can go either direction with the pink vector, making it very, very long. And then with the green vector, I can move it around this pink vector, and that will allow the vector to reach all of these little points. So the green vector with the pink vector can reach every single point on this plane. So if I scale the green vector like I did here, I did it by 3 just to show how many more points I can reach. And the scales can be literally anything. For this next step, I'm going to be showing the linear combination of these two vectors algebraically. So first I'm going to put it into vector notation, and I'm having my k and c represent constants, and then I'm going to use the systems of equations to rewrite these vectors and then solve for my unknown values of b, a, c, and k. So then k is going to be equal to 3c minus 5a. And now since we found k, we can define k as a product of c and a. So basically I can put any c value and a k value, and because a can be anything, I can solve it. So I'm going to just have an example here. And then my a value can take where that c value is missing to find that k. And then b is just a product of, well, a combination of c and a values. So b can also be anything, but it doesn't depend on k because I've defined it up there. And now for another example, I'm going to have k is equal to pi, just to show that it can be any number, and then I'm going to have c is equal to the natural log of 7. These are not easy, nice numbers, but using this formula I created algebraically from systems of equations, I can figure out that the span of this set of vectors is all possible linear combinations, and that's just because of my found value of k, c, and then b and a. But as I solve for a, it's going to get pretty irrational, but like any point on that plane can be defined by these two vectors algebraically as well. Just a little bit harder of an example. So if these three vectors can be equal to 0, where a, b, and c are not equal to 0, then Gauss can hide from us. This is because it will become, the range of the vectors will become a plane in R3, so it will be like this slanted plane potentially, depending on the vectors. But here I'm just setting so that way a, c, and b, and I'm trying to solve to find c and b. So if c can be equal to anything but 0 for this, then it's going to be false. So I'm going to put c is equal to 1 because that would be the lowest numerical value of c. So if this works out, then the very last one would be equal to the b value. So I'm going to plug in a is equal to 2, b is equal to -1, and then c is 6, which it did work. So they are linearly dependent. So vector 6, 3, 8 is a linear combination of the other vectors. So the range that we can find him will be limited. And we could always change this, and a way to change this is making that last part of the vector not equal. So here what I'm going to do is I'm going to make a little sad face because it's no longer going to be equal. I'm going to have a is plus 6c minus 6b. So when I do this, I'm going to get 8 is equal to 6, and that would be impossible. So therefore it would be impossible for Gauss to hide from us.